All right. So today we are going to start a new chapter, and the chapter is named as Seismology. Okay. And if I I know this is a new word for you. So what seismology essentially means is the study of the elastic wave propagation through the earth. Okay. Elastic wave propagation through the earth. Okay. That's what we are going to see. Now, traditionally, seismology is based into two parts. One we call as earthquake seismology, and the other one is called exploration seismology. Okay. So, can someone tell me how fundamentally an elastic wave is generated? So, if I ask you to generate an elastic wave right now, can you do that? And how would you do it?
By stretching a string and plucking it.
Okay. Any other easier? So, suppose you don't have a spring with you. Okay. Right now, you are sitting in front of your desk, and I want you to create a seismic, an elastic wave. What would you do? You know the answer. Come on. What would you do? So if I simply bang on my table,
Yeah,
okay,
just tap
Yes,
on the
sir.
table.
yeah, so that creates a seismic, that creates an elastic wave, right? So the fundamental of elastic wave generation, so generation and then of course propagation, generation and propagation of elastic wave. The fundamental lies in elastic collision, right? I'm sure you know what elastic collision is. So by banging on my table, I am creating an elastic collision, and then suppose you are sitting on the other side of the table, you feel that vibration, right? And that happens because the elastic wave is propagating through this media of table, you know, and it is going towards you because you are sitting on the other side, right? So that part is propagation. So in both cases, elastic collision is involved, right? So the very fundamental part of elastic wave propagation is around elastic collision. And elastic collision highly depends on the elastic property of the medium, okay? Property of the medium in which it is being generated and through which it is propagating, right? Through which the wave is propagating. So the nature of the elastic wave would primarily depend on the elastic property of the medium. Okay. So before we actually go into the actual seismology of be it earthquake seismology and be it exploration seismology, we must understand some of the fundamentals of elastic wave propagation and the elastic properties of of the different earthy materials that I'm interested in. Okay. Now, you might ask, what is the difference between earthquake seismology and exploration seismology? Now, fundamentally, they are very same. They both are based on the propagation of elastic wave. Now, in case of earthquake seismology, the source, what do I mean by the source? Say, for example, when I am banging on the table, this bang itself is the source. Okay, that is where I am propagating, I'm starting my elastic wave, right? So the source in case of earthquake seismology is generally natural. That means I create an earthquake. You all know what earthquakes are. So when I create an earthquake, you create an elastic collision. And because of that elastic collision, you have this seismic waves, as we call them. Okay. And that propagates through the earth. The study of that is called earthquake seismology. Okay. So here the source has to be natural. Okay. Now, in case of exploration seismology, what essentially you do, you create such vibration anthropogenically or manually. You create such vibration. Okay, so the source has to be man-made. Okay, man-made, or you can say anthropogenic. So what you can do, suppose you kind of dig a small hole in the crust. Okay, maybe 2 or 3, maybe 1 meter deep hole, and you put some dynamite inside. Okay, and you have a controlled blast. Why I'm saying controlled? Simply because you don't want the dynamite to actually break everything around you, right? The force of that dynamite has to be controlled so that it creates enough vibration for your purpose, but then it should not be so large that it actually destroys your surrounding, right? Hence, we are saying it is a controlled blast. So you actually blast, kind of blast a dynamite, and you generate the source by yourself. Okay? The other way of generating such source is maybe you have these huge hammers, I mean, which are actually carried in big large trucks, and you pound those hammers very rapidly on the ground. Okay, so hammering on the ground. Okay? Hammering on the ground with very, very, very large sort of weight, if you like, okay, which are carried generally on truck, through which also you can create seismic wave. You can create another source. Now, why would I actually want to create these seismic waves? Okay, why would I generate these elastic waves? Because based on the reflection and refraction of these seismic waves through the different layers of the earth. Okay, so what generally happens that we will read about this in much more details. Of course, if I generate seismic waves at this point, and maybe we have several layers on the on the earth with different elastic properties, what would this seismic wave do? It will get reflected. Some cases it gets reflected back. And if I have receptors here, based on certain parameters, I can actually image subsurface. I can create an image, actually an acoustic image. Acoustic means, these elastic waves are nothing but like very similar to, I mean, it's in the same frequency of sound waves, right? So elastic acoustic image of the subsurface. Okay, so because you cannot see through the earth, because you cannot really penetrate through the earth, what you can do, you can use this technique of controlled blasting, and then studying the reflection and refraction pattern of of such elastic waves, and you can image the subsurface, acoustic imaging of the subsurface. Okay, it's very similar to your ultrasonography. Ultrasonography is done often to find out the status of the fetus inside mother's womb, right? Similarly, ultrasonography is used to understand how your internal structure. For example, you want to see how the liver looks like for a particular person. Okay, you can have that acoustic image of the liver by doing ultrasonography. So the fundamentals are very similar to seismic imaging. Yeah, the only difference is, I mean, there are many differences, but one of the fundamental differences in case of ultrasonography, it's the ultrasound that is used. It's not the sound that you can hear, or but in this case, of course, the elastic wave which is propagated is very much perceive. You can perceive that wave. Okay, so this is what we call as exploration seismology. So the difference between exploration seismology and earthquake seismology is generally the nature of the source. In one case, it is natural. In the other case, it is controlled or created or man-made. Is that clear, guys? Understood? Any question?
Yes, sir.
Okay. Now, so we said that the secret lies in the elastic properties. Okay. So before we get into the elastic properties, we have to understand few things. And the things are that, the things that we need to understand before we get to elastic properties are called stress and strain. And the relationship between stress and strain would lead to the elastic modulus. Modules, rather. Okay, that means we have to first understand what do we mean by stress, what do we mean by strain, and then how the relationship of stress and strain works. That would lead to understanding of elastic modules. And elastic modules generally, control the elastic properties of a particular medium. Okay. So the first thing then we have to understand is stress. Right. Now we are not talking about the stress that you guys feel before an exam. Okay, that's not we are going to talk about. We are also not going to talk about the environmental stresses that happens because of extra carbon dioxide in the nature. Okay, we are going to talk about stress that is purely mechanical. Now, if we want to understand the concept of stress, what we need to understand is the concept of force. Okay, and you know that force is generally expressed with this very fundamental equation: P is equals to mf, right? Where P is the force, applied force, m is the mass on which the force is applied, and f is the acceleration, right? That is the change in acceleration of that particular mass m, and that is expressed P is equals to mf. It's a very fundamental equation from Newton's law. Now, force, let us say I have a chalk, okay, and this is put on a table, okay? Imagine with me. Okay. Now, I ask you to actually apply some force on this chalk on one side. What would happen to this chalk? This chalk will, kind of translate from or rotate from point A to point B. Okay. You can do that, right? Without breaking the chalk. Is it possible? Yeah.
Yes,
So
sir.
such forces, okay. So what is fundamental in this type of application of the forces? The application of such force is that suppose if I look at this chalk, okay, and suppose I have 2 points x and y, which has a distance maybe r, okay. So at position A, the distance between x and y was r, and at position B, the distance between x and y remain r, right? So there is no internal deformation within this chalk, okay, or within this material. The material, by the application of this force, the whole material is translated or rotated from one place to the other. Okay, so there is a body movement of this whole material, and application of such force is called body force. As if the force is being applied all over the body. Okay, is it clear? Now, suppose I ask you to drop that chalk from your hand on the floor. Okay, if you do it from a considerable height, what you will find, once this particular chalk hits the ground, what happens to this chalk? The chalk essentially breaks, right? Maybe 2 to 3 pieces or so, right? Now, suppose if I ask you that the distance x and y, the relative distance between x and y is completely hampered. So this was r before, and they remained r after the application of body force. But in this particular instance, where at the end of this of the application of the force, there is an elastic collision, and the elastic collision is rapid enough to actually, or strong enough to actually break this rock, so break this material, and this relative position of x and y is disturbed. Okay, the material breaks. Okay, and such force is called surface force. Okay, so now stress is defined as and stress is generally designated with a letter sigma, is equals to F by delta S. Okay, where F being, so Fs I can write, Fs is actually your surface force. So surface force per unit area, yeah, surface force per unit area is termed as stress. Okay. Now, what else is force per unit area? Can you tell me what else is force per unit area?
Yes, sir.
Pressure. So pressure is also force per unit area. Now, so for that particular reason, stress and pressure has exactly the same units. Okay, so force and pressure have same units. Now, in case of earth science, force and pressure is generally used in a bit of different connotation, with a bit of different connotation. How? Generally, stress is thought to be anisotropic. Stress is anisotropic. Okay. So anisotropic means, how do I express stress? With what sort of figure? What sort of geometrical figure should express stress then? Huh? Tell me. If it is anisotropic means the value of stress is different in all directions. Then how would I express that? With the help of an ellipsoid, right? Because it is anisotropic. So there will be one direction, there will be maximum stress. In one direction, there will be intermediate stress. And in the third direction, there will be minimum stress. Okay. So stress is anisotropic. And generally, pressure, which is it is thought to be exerted by fluid. So you can write this to be fluid pressure as well. Okay. Is isotropic. So as if, I have a balloon and then I have pumped that balloon, okay? Or I have pumped that balloon with water or so. Okay. So then what happens? The force exerted on the balloon wall from all sides, it's equal. Right? So pressure, which is generally referred as fluid pressure, that is in earth science generally thought to be isotropic, whereas stress is regarded as anisotropic. Some fundamental, some very commonly used units for stresses could be bar, of course, PSI. Yeah. Then Pascal, megapascal, gigapascal, and all the kilopascal, all the derivatives of Pascal. So all these are units for stress. You must find out what are the mutual relationship between them. Okay. Now, did you understand what is stress?
Yes, sir.
All right, very good. Now, let us say stress is also reactive. What do I mean by that? So, suppose I am applying on this surface force from this side, okay? So, force is towards this surface, right? So, I will draw my stress as a reaction to this force, okay? So, the stress will be directed opposite to the force, yeah? So, because it's thought to be a reaction to this force, okay? So, now stresses could be generally, broadly subdivided into compressive stress and tensile stress. Tensile stress or extensional stress, okay? Same. So compressive stress means that I have a material and I try to compress it with the force. Okay, this is compressive stress. Now this is force, right? So how would I draw these stresses, compressive stresses? The compressive stresses will be like this. Okay. So this is compressive stress. Now extensional stresses, because this is reaction, right? Extensional stresses, the force, I have to extend this body, right? So this will be like this. This is the force. So how would I draw my stresses? You see, this is counterintuitive, huh? So compressive stresses has the directions which are like going away from the body, right? Because the forces are coming in. That would compress my body. So the compressive stresses are oppositely directed, away from each other. Whereas tensile stress, which the forces are actually pulling it up, pulling this body up. So hence the stresses are oppositely directed. Okay. Is it clear? So this is stress. The blue is stress, sigma. For earth science, compressive stresses are thought to be positive. Okay. So if I just write down 20 megapascal plus 20 megapascal, that means we are talking about compressive stress. And tensile stresses are thought to be negative. The sign convention is tensile stresses are regarded as negative stresses, and compressive stresses are regarded as positive stresses, because you will find out later on when you study structural geology, hopefully by me or by someone else, what you will find out that most of the stresses that acts in the earth are generally compressive. Okay. Hence, because most of the stresses are compressive, we have to use a convention which is positive for compressive stresses. Okay. But tensile stresses, because they are less frequent in nature, hence we associate negative annotations with them. Okay. Negative sign convention with them. So compressive stresses are positive, tensile stresses are negative in earth science. Now, if you are an engineer, okay, if you are an engineer, this is different. So they treat tensile stress as positive and compressive stress as negative. This is for engineers, mechanical or civil engineer. Now, if you read a document which is written by an engineer, okay, or if you in your career, if you interact with an engineer, you have to be very careful with this stress convention. Okay, whether if they are talking about positive stress, that means that they are talking about tensile stress. Okay, they are not talking about compressive stress, because tensile stress, what does this do? If I extend this material, what would happen? This material will be enlarged, right? So hence they say, this is positive stress. If I compress anything, what would happen to this body? This body will be like squeezed. You are trying to squeeze the body. Hence they are associating compressive stress with negative annotations. Is that clear? So once you interact with an engineer, if you read the engineer's document on stress and strain, they are fundamentally, everything is the same. Okay, there is no difference in science. It's after all mechanics. Okay, with what we are using, what they will be using. The important thing that you have to remember, that they have just a different sign convention. Okay, and the way science is progressing nowadays, of course, you as a simple earth scientist will not be able to survive. If you choose to do a job in the industry or be in academics, you have to interact with people from different branches. Okay, things are becoming multidisciplinary every day. So this is one of the lessons which you have to remember, that you have to communicate in their language. So what you have to fundamentally do, that to translate your positive information into negative connotations if you are talking about compressive stresses, and vice versa for tensile stress. Is that clear?
So what's the logic of earth science sign convention?
Yeah, because we most of our stresses are compressive. We mostly deal with compressive stresses. So think about, in everything that in all our calculations, if we have to use negative connotation, is that intuitive? It's not, right?
Yes, sir.
So hence we use positive for compressive stresses. Okay. Now, compressive stress, tensile stress. Now suppose I have a surface on which I'm providing some stress. So what sort of stress is this? Compressive or tensile? Hmm? This is compressive or tensile? By the looking at this sign of this arrow,
Compressed.
compressive, because it is going away, right? This can be actually resolved into two components. One is perpendicular to the surface, which we will designate as sigma n, or tensile stress or normal stress. Okay, and there will be one component which is parallel to the, I can resolve the stress, one being parallel to the surface, and that is designated as tau, or shear stress. Sorry, shear stress. Okay, so we have talked about compressive stress, tensile stress, normal stress, and shear stress. Okay. Now, suppose we wish to define that a state of stress at a point P, okay, on which this stress is acting, and I want to resolve it in 3 dimensions. Okay. So to do that, what I'm doing, I'm essentially defining a coordinate system. Okay. I can do X, Y, Z, but to just follow the convention, let us say these 3 mutually perpendicular coordinates, Cartesian coordinate system, I refer them as 1, 2, and 3. And then I want to express this stress, which is sigma, on this particular point. So how would I do that? I will do a very smart job, that I will essentially consider a cube surrounding that point. Okay. So consider a cube surrounding that point, so that this point is actually at the center. Okay. I should have actually drawn the cube a little bit differently, but never mind. Just, you all are my friend. I'll just put the P here. Okay. So I'm considering a cube which is at the center of that cube. I have my point P. It's an imaginary cube. Now what I will do, I will resolve this stress sigma, okay, on each of these surfaces, okay, or these 3 mutually perpendicular surfaces. The rest of them are mirror images of them, right? So if I want to resolve this, I can resolve it in many different ways, but one of the ways of doing of resolving it could be, one, normal to this surface, okay, this surface, and 2, parallel to this surface. Okay, one is along sigma, one is along 3, axis 3, the other one along axis 1, and the third one is along axis 2. Okay, let us say then this one to be, so let us call this as sigma 1, 1, No, sorry, I'm making a mistake. Now let us say this let us name these three planes. Suppose the plane which is perpendicular to the axis 1, let us name that plane as 1. The plane which is perpendicular to axis 2, let us name that plane 2. And the plane which is perpendicular to axis 3, let us name that plane 3. Okay. So now this particular component will be then sigma 3, 3. This one will be sigma 3, 1. And this is sigma 3, 2. So that means you see the first number we are putting as for the plane, and the second number is put for the axis. Okay. Similarly here, the first number is put for the plane and the second number is put for the axis. Similarly here, the first number is plane, the second number is axis. Similarly, I can have three components here too. One parallel to 3, other parallel to 1, parallel to 2. Now you see the one which is parallel to 2 is normal to the plane. So this is sigma 2, 2. This is sigma 2, 1, and this is sigma 2, 3. Okay. Similarly, I can also have three components here. So fundamentally, then I can express this total state of stress, okay, as sigma 1, 1, sigma 1, 2, sigma 1, 3, sigma 2, 1, sigma 2, 2, sigma 2, 3, and then on the so this sigma 1, 1, sigma 2, 1, 2, and sigma 1, 3 will be for this plane, right, which is perpendicular to plane 1, and then sigma 3, 1, sigma 3, 2, sigma 3, 3, right. Now you see, because I have already defined these the direction of these axes, all these units, all these components are actually scalars. Okay, all these components are actually scalars. So to express stress, I will need 9 scalar components. Okay, so to express stress in 3 dimension, I will need 9 scalar components. Okay, so that means in 3 dimension, it is 3 square. If dimension is 3, so that is 3 square. Hence, stress is termed as a tensor of rank 2. So hence stress is termed as a tensor of rank 2. Similarly, for a vector, any vector, I will need how many components do you know I need for a vector in 3 dimension? How many components do I need in 3 dimension? How many scalars do I need to express a vector in 3 dimension?
3 components.
3, right? So hence, so suppose any vector, I need 3 components, that's 3 to the power 1. Hence, any vector is thought to be a tensor of rank 1. Okay. Rank 1. For a scalar, how many components do I need in 3 dimension? 1, right? Isn't it?
Yes, sir.
So that is 3 to the power 0. So hence, scalar is called a tensor of rank 0. Okay. Scalar is a tensor of rank 0. Now, say that's why if I want to express things in 2 dimension, so in 2 dimension, if I want to express stress, how many components would I need? How many scalar would I need? Huh? If the dimension is 2, then how, if for stress, it is a tensor of rank 2, how many components would I need? Huh? Tell me quickly. Huh?
4 component.
4, 2 square, right? That's why 4. So tensor is then, that's why we call tensor to stress is a tensor of rank 2, because I need 9 components to express stress. Okay. Now tell me, if I look at this matrix, okay, tell me this sigma 1 1, so sigma 1 1, sigma 2 2, and sigma 3 3, what type of stresses are they? Normal or shear?
Normal.
Normal stresses. How about the rest? Sigma 1 2, sigma 2 1, sigma 1 3, sigma 3 1, sigma 3 2, sigma 2 3, sigma 3 2.
Shear.
They are all
Shear.
shear. Okay. So it has 3 normal stresses and 6 shear stress. Okay. Now you can imagine, suppose I have one stress sigma 1, not sigma 1, say sigma a, sigma m, suppose one stress sigma m and another stress sigma n. Okay. And all of them, this has 9 components, this has 9 components. And if I ask you to do any operation with them, yeah, is it going to be easy or not? If I have 9 components for sigma m and 9 components for sigma n, and I ask you to do any stress operations, okay, add them, subtract them, or whatever, I multiply them, would it be easy?
No.
No, it's very difficult, isn't it? So we need to find a way of kind of reducing these components. Okay. So what we will do, we will now start rotating this cube. Okay. We will start rotating this cube. So what would happen if I start rotating this cube? Do you think that the values, the magnitudes of all these components will remain same, or they will change if I keep on rotating this cube? They'll stay same or change?
So they will change.
They will absolutely change, because I will resolve my components in a different way, right? So while rotating, so now I am rotating my cube, and there will be a point when sigma 1 2 will be equal and opposite to sigma 2 1. There will be a point where sigma 3 1 will be equal and opposite to sigma 1 3, and there will be in that same position, it's the beauty of the nature, and at the same position I will find that the sigma 3 2 will be equal and opposite to sigma 2 3. Okay, and they will be cancelling out with each other. So now I am at a position where I have rotated my cube. This is my rotated cube, huh? I have rotated my cube in such a way that all these shear stress components are actually nullified against each other. And what we are left with is sigma 3 3, sigma 1 1, and sigma 22. Okay. So all my shear stresses are nullified. Then how would I write this matrix? I'll write this matrix as sigma equals to sigma 1 1 0 0 0 sigma 2 2 0 0 0 sigma 3 3. Right. And then I will be very clever, and what I will do, I will redefine my axis. I will redefine my axis. So this is my axis 3, this is my axis 2, this is my axis 1, or 3 prime, 2 prime, 1 prime. Okay. So what I am doing now, I have rotated my cube. I have got rid of all my shear stress component. I am left with only 3 of these beautiful normal stress component, and then I am saying I am redefining my coordinate axis system. Okay, which is parallel to sigma 1 1, sigma 2 2, and sigma 3 3, and we call them as principal axis of stress. Okay, and the sigma 1 1, sigma 2 2, and sigma 3 3 are called my principal stresses. So if we choose the coordinate system correctly, any stress can be defined only by 3 normal stresses. Okay? If I choose my coordinate system correctly, I can express this 9 component, I can reduce this 9 component stress to a 3 component stress matrix. Okay, and that is way more convenient in dealing, right? So now I only have 3 stresses, sigma 1 1, sigma 2 2, sigma 3 3. Because I have only 3 stresses, I can even get rid of this suffix. Okay, sigma 1, sigma 2, sigma 3. Let's just get rid of them. Why do I need them anymore? Okay, I'm simplifying things. And then I have, 1 prime, 2 prime, and 3 prime. If I forget the rest of the story, I can also get rid of these primes. So I have these 3 axes now, this principal axis of stress, along which there is no shear stress acting. It's a very unique situation where there is no shear stress acting. Now, lucky for us, in the Earth, this rotated 3 axis, So this is the sigma 1, sigma 2, and sigma 3. Okay. So this rotated stuff, sigma 1 prime, sigma 2, and sigma 3, So 2 of them are horizontal, 1 of them is vertical. So ideally, if I look at the Earth, so I can have one vertical axis, suppose we call them as sigma V, and then I have sigma capital H and sigma small h. Sorry. Let's use a different color. Sigma V, sigma capital H, sigma small h. Okay. So lucky we are that these principal stresses in the Earth, 2 of them are horizontal, 1 of them is vertical. Okay. So the principal stresses on the Earth, this is how they are. 2 of them are horizontal, 1 of them is vertical. It is not like the vertical. It's not like the principal stress is, at an angle to the verticals that makes our life even more difficult. It's not. Okay. So this sigma V is called then the vertical stress. Sigma capital H is called the maximum horizontal stress. and sigma small h is the minimum horizontal stress, which are nothing but, sigma 1, sigma 2, and sigma 3. Okay. So they are my principal axis of stresses. So these are my principal axis of stresses, and these are my principal stresses. In the earth, we just name them differently. Sigma V, vertical stress, sigma capital H, maximum horizontal stress, sigma small h, minimum horizontal stress. Okay? Any question?
Sir, why there is no shear stress? Means is this only due to our own convention we have taken such coordinate? Or?
No, it's that's how, I mean, suppose I'm piling up a brick of rocks. Okay, so there are bricks, right? I'm just piling them up. So what would the force be here is the weight of these rocks, right? Weight of these bricks. That would create the stress, isn't it? So
Yes,
now
sir.
think of this particular plane. Where would the shear stress come from? The forces are acting perpendicular to them. So if I have a plane which is like this, then only I will get the shear stress. Now, it has to have an angle. Any plane which is parallel to a stress or any plane which is perpendicular to a stress, that will not have any shear stress.
So, sir, naturally we will have only principal stresses.
Naturally, I mean, if the plane is horizontal and if the planes are vertical, we will have only normal stress. But if the plane is inclined, we will have shear stress. Now, suppose I have this beautiful, say this is the crust, okay? The vertical stress. Suppose I have a fault here. Will there be shear stress on this or not?
Yes, sir.
Absolutely. So because the surface of the earth, okay, and the layers, they are like, piling up above one another. The planes are horizontal, conceived to be horizontal. Hence, and because the stress is being generated because of the weight of the rock. Hence, these principal stresses are horizontal and vertical. Okay? But any plane which is not horizontal or vertical will have a shear stress on it. Okay? Unless you have shear stress, there will be no deformation. You will find that later on. There will be no faulting, there will be nothing. The earth will stop eventually. But the only point you have to remember at this moment that the three principal stresses, two of them are horizontal, one of them is vertical. Okay, any other question? All right, so I think this is a good place to stop right now. We will continue with stress and strain in the next class. But do you mind doing this class also in live mode? Because it's important that you interact with me. Is it okay? Or, I mean, you have the right to have a pre-recorded lecture, but it's up to you. Tell me. What would you prefer?
So live will be good.
Live will be good.
Like,
Now, everyone agrees, right?
yes, sir.
Okay. Otherwise, it's I don't exactly understand whether these concepts are very important to be in your mind. I mean, completely clear in your mind. I don't always understand whether you are getting it or not. Okay. So if it is interactive, I'm more happier that at least I'm able to communicate to you. Okay, so then let's do a live class on well, when it is Wednesday. Okay, and I will also try to finish your quiz copy check by then. Hopefully, if not, maybe sometime later during that week only. All right, so I will see you on Wednesday then. Thank you very much.